Okay, this screencast is on periodic trends for AP chemistry. So we're going to start by talking about this idea of an effective nuclear charge. But first, I want to remind everyone about Coulomb's law. The force of attraction between the negative electrons and that positive nucleus is the basis for the structure of the atom. The force of that attraction, now that could be repulsion if those charges are the same, is governed by Coulomb's law. So on the AP chemistry level, we're not really going to be doing these calculations and actually calculating the force. What we're going to be doing is using Coulomb's law because we understand it to explain the structure of the atom. We must always be aware of that attraction between the positive nucleus and those negative electrons. And again, so that force of attraction or repulsion is going to be equal to the size of the two charges. And divided by the distance between those charges. So when we look at explaining the structure of the atom, think about the distance between the two charges. How far are the electrons away from the nucleus? You also want to think about the size of those charges, the difference between the protons, number of protons or positive things, and the number of negative things in an atom. All right. So effective nuclear charge. So the attraction of the electrons to the nucleus is dependent upon the nuclear charge, how many protons are present, and the shielding effect of the inner electrons, those core electrons. This is the extent to which the core electrons protect the valence electrons from that positive nucleus. So these two factors together are referred to as effective nuclear charge, or ZEFF, ZEF. This is the pull by the nucleus each electron experiences. So this takes that shielding into account. So if we think about, this would be a sodium atom, we've got 11 positive protons in the nucleus, and if it's electrically neutral, we have 11 electrons outside of it. But really a better way to think about this would be that, yeah, we've got 11 protons in the nucleus, and we have 10 core electrons. So those core electrons are kind of running interference between the attraction of that one valence electron that sodium has and its attraction to that positive nucleus. The 10 core electrons are going to shield it from feeling the full power of its attractiveness. So that attraction is, again, effective nuclear charge. And we can use that as an explanation in some of our trends, or for some of our trends. So again, it's the protons, but you got to take into consideration the shielding by those core electrons. All right, so polyelectronic, we can use this to predict patterns, especially if we can see how it works on the periodic table, can use the amount of energy it takes to remove an electron for this. So really, when we talk about this pattern of effective nuclear charge, we're going to be talking about the ionization energy, really. So that's the energy necessary to remove an electron from a gaseous atom. The higher the attraction of that electron to the nucleus, the higher the ionization energy. The lower the attraction of that electron to the nucleus, the lower the ionization energy. All right, so we've talked about shielding. The electrons on the higher energy orbitals, energy levels tend to be further out because they have to look through the other electrons to see the nucleus or to experience the attraction of that nucleus. So they're less affected by the nucleus, and so they create a lower effective nuclear charge. So here's a nice little picture. You can look at these outer electrons right here and their attraction to this nucleus. They're experiencing this attraction, but they're also experiencing here with these red arrows repulsion between those other electrons. So while the nucleus is pulling that outer electron in, the other electrons, those core electrons, are pushing the electrons away. So that's another way we can think about shielding. All right, so penetration. There are levels to the different, or to the electron distribution for each orbital. That's because they have different shapes, or because they have different shapes, they have different electron distributions. So an S sublevel is the name that we gave for a sphere-shaped area of probability. Now, these S electrons are more attracted to the nucleus than the P electrons are, for example. And that's just because of the shape. That sphere shape allows those electrons to reside closer to the nucleus. And so, again, the closer they are to the nucleus, according to Coulomb's law, the more attracted they are going to be. That dumbbell shape doesn't allow the electrons to exist closer to the nucleus, so they're not as attracted. And that's why an S orbital always fills before a P orbital. So again, we're talking about these different shapes. We have that sphere for the S sublevel, that mathematically drawn area of probability of where an electron is most likely to be found. It's more of a dumbbell shape when we get into the P sublevels. So again, these orbitals are of equal energy. They just have different orientations in three-dimensional space. And that's also the reason we draw 2 or 3 sets of parentheses when we're doing the orbital diagrams for a P sublevel. And then D has 5. Most of those look like that 4-leaf clover, except we got this weird one right here. And F, again, we have 7. All right, so the outer energy levels penetrate the inner levels, so shielding on the core electrons is not totally affected. They're still attracted to that positive nucleus. From most penetration to least penetration, the order is the S sublevel. The electrons in that S orbital are allowed to can penetrate through the shielding more than the P sublevel, which can penetrate more than a D sublevel, which can penetrate more than an F sublevel. So those that can penetrate through the shielding more are more attracted to the nucleus. All right, so let's get more into these periodic trends. And here's kind of just a short little explanation of those periodic trends. Again, on the AP level, they expect you to know this. They're just going to ask you to explain the things on why this is. And they're also going to ask you to explain some of the inconsistencies with general trends, because that's really what they are, just general trends. But we'll learn how to deal with those different types of questions. Okay. So we're going to start with atomic radius. Here's a nice little visual representation of the atoms of the periodic table. And we can see a general trend. As you go from left to right across the periodic table, you can see the general trend is that the atoms get smaller. And we'll talk about the explanation for that, but here we're just going to look at what the trends are. And as we go down the periodic table, we know that the atoms do get larger. And again, that's a general trend. We can see some differences here that will maybe be exceptions to that general trend. All right, in general, as you decrease, as you go across a period, so as you go from one side of the periodic table on the left to the right, we have a decrease. Well, what's happening there is that you end up with more protons. And those more protons in a nucleus are going to increase the effective nuclear charge. Now, the shielding is going to remain constant, because as you go across the periodic table, remember each period on the periodic table corresponds to an energy level. So if we're going across the periodic table, every single one of these atoms has 3 energy levels for this period, to be exact. So all we're doing is really the number of protons are changing. The amount of shielding is going to remain constant. So we do have an increase in that effective nuclear charge. And so since there's an increase in the effective nuclear charge, the electrons are more strongly attracted to that nucleus, and the electron cloud is being pulled. Okay, so again, as you go across a period from left to right, you end up with more protons because electrons are still on the same energy level. So we have an increase in effective nuclear charge, which means that the electrons are more strongly attracted to the nucleus, and that attraction pulls the electron cloud closer to the nucleus, and that's why the atoms decrease in size as you go across the periodic table. Increase as you go down a group. So the increased number of energy levels, which again we're going to use as lowercase n, increases the distance over which the nucleus must attract and therefore reduces the attraction for the electrons. This reduced attraction allows the electron cloud to expand, causing the atoms to be larger as you move from top to bottom on the periodic table. All right, now the size of the atoms can also explain a lot of other things. So in our next periodic trend, we're going to kind of look at ionization energy. Ionization energy is the energy required to remove an electron from a gaseous atom. So if the electrons are really strongly attracted to the nucleus, you're going to see an increase in that ionization energy. Highest energy electron is going to be removed first. So these are usually going to be on those outermost energy levels. First ionization energy, we would notate that with I and then sub 1, meaning we're removing the first electron from an atom. And then we would say second ionization energy, I2. So that means we're removing a second electron from the atom. I3 would be if we are removing the third, I4 removing the fourth electron from an atom. So each time you remove an electron from an atom, the ionization energy increases. Remember, this is all about the attraction of the electrons, those negative electrons, to the positive nucleus. So if you remove one electron, overall you have more positive things than negative things. And so those remaining electrons are going to be more attracted to the nucleus. So I2 is always greater than I1. I3 is always greater than I2. But sometimes there are big jumps in ionization energy. So we can look at something like for magnesium. So here we're just looking within the same atom. I1 for magnesium is relatively low. It's going to take energy because you're removing those negative electrons that are attracted to that positive nucleus, but it doesn't require a whole lot of energy. It takes about double the amount of energy to remove the second electron. But when you go to remove that third electron, the jump in numbers is really, really huge. So something must be going on here within an atom that would cause this massive jump in ionization energy. And if we kind of draw out a pretty middle school look of an atom, just to kind of highlight the number of electrons in each energy level. When we're removing for I1 and I2, we're removing these electrons, these valence electrons. And so they're both relatively low, but when we go to remove I3, or for I3, we're removing an electron that is much closer to the nucleus and experiences less shielding. And so that would explain why there is a big jump in that ionization energy, because we're removing a core electron. So the effective nuclear charge increases as you remove electrons, because you still have the same number of protons. And it takes more energy to remove a core electron than a valence electron, because the core electrons are closer to the nucleus. And according to Coulomb's law, the force of attraction is greater, requiring more energy to remove that electron. All right, so see if you can explain this trend for aluminum. I1 still relatively low. I2, I3, and oh my goodness, 11,000 for I4. How would you be able to explain the difference between the big jump in ionization between I3 and I4? Well, again, aluminum has 3 valence electrons. And so I1 corresponds, I1, I2, and I3 correspond to removing one of these 3 valence electrons. When we go to removing that 4th electron, it is a core electron. And core electrons are more attracted to the nucleus because they are closer to the nucleus and experience less shielding. Okay, that is a good example of a type of question that you might get on the AP exam, just talking within an atom. Let's talk about a comparison of atoms on the periodic table. So as we go from left to right on the periodic table, you see an increase in ionization energy. So again, remember we're talking about things that have valence electrons on the exact same energy level as we go across a period. So what is changing? More protons, and as you go across the periodic table from left to right, an increase in effective nuclear charge, which means the electrons are more strongly attracted to the nucleus. It's almost the exact same reason that the atom is larger. Is smaller than as you go across the periodic table. More attraction, so it's going to require more energy to remove an electron. It decreases as you go down a group. The reason for that is you get an increase in the number of energy levels, which increases the distance over which the nucleus must pull and therefore reduces the Coulombic attraction for electrons. So those electrons aren't as attracted to the nucleus just because of the distance, according to Coulomb's law. Okay, so we have our general trend now. Now let's look at some of these others. And we've learned a lot about the different explanations that we have here. So we can see the periodic table. Here we're starting with hydrogen, and then we go to helium, and the ionization energy increases because we're going from left to right across the periodic table. That follows. And then the ionization energy drops. And so we need to be able to explain why the ionization energy of lithium is lower than that of helium. Well, the reason for that is because lithium has valence electrons in the second energy level, but helium has electrons in the first energy level. Those valence electrons for helium, are more attracted to the nucleus because they are closer, according to Coulomb's law. Lithium has electrons in the second energy level, so there's a greater distance between the nucleus and these valence electrons, resulting in less attraction. Okay, so what we have now is, I'm going to get to that in just a second. Oh, and helium it has a higher ionization energy than hydrogen because they are on the same period of the periodic table, which means that these guys have the same valence electrons in the same energy level, but helium has more protons in the nucleus, so it has a greater effective nuclear charge, meaning the valence electrons are more attracted to the nucleus, resulting in a higher ionization energy. Okay, so now we would expect that same trend to happen, and in general it does, but we got a couple of other little blips here. So as we're going across the periodic table, now we'll bring that in, we can see we've got hydrogen and helium. Then we've got lithium and beryllium. And as we're going across the periodic table, we can see ionization energy increases. And then we get to boron. But look at what happens here. Boron actually has more protons in the nucleus, but it ends up with a lower ionization energy. So how can that be? Well, what's happening here, if you'll notice, this periodic table is color-coded into the different blocks of the periodic table. So we've got our S blocks here that are, I guess, kind of minty green. We've got our D block elements here in gold, and here the salmon color is our P block elements. So the electron configuration of beryllium has a full S sublevel. Here we have a first electron in a p sublevel. The reason that there is a lower first ionization energy for boron than for beryllium is that the electrons must be less attracted to the nucleus. That's the only explanation there is. So what could account for that? That would be the penetration between the S sublevel electrons. Remember, they can penetrate through the shielding more and are more attracted. But here I have boron, which has one electron in the p sublevel, and the p sublevel electrons cannot penetrate through the shielding, so they're less attracted, which means a lower first ionization energy. But then the trend kind of picks up, and as we go across the periodic table, we see that carbon's ionization energy increases and nitrogen's, but then oxygen's is lower than nitrogen. And that's weird. That goes against our general trend. So something must be happening here in the structure that causes this eighth electron of oxygen to not be as attracted to the nucleus as the 7 electrons in nitrogen. So even though oxygen has one more proton, so it should be more attracted. Well, what's happening here, if you think about your orbital diagrams, as we're filling in, let's say, 4 electrons into our p sublevel, what we would do is we would write 1 S, let's see. Actually, what we would do, I think I can erase there. Okay, let's just do the valence electrons. We've got 2 P4 for oxygen. That wanted to be a 7. There we go. Okay, so we've got our parentheses, our 3 orbital orientations. And I'm really not good at drawing with the mouse. Okay, so it's going to be up, arrow, up, because of Hund's rule. And this one is also going to be up. Well, that would be what nitrogen ends with. But then oxygen, because it has 4 in the p sublevel, is going to have the first electron right here. Here we have 2 electrons in the same orbital orientation. So these 2 electrons, which are both negatively charged, are going to repel each other. And that repulsion actually causes the charge, or kind of the that repulsion actually works against the attraction of those electrons to the nucleus. And therefore, that electron, that last electron for oxygen, is less attracted to the nucleus because this other electron wants to get rid of it. So when we start to have these, the first paired electron is going to be less attracted to the nucleus because it's being repulsed by the other electron there. All right. So we can see that this trend is going to continue. Let's see, I'm going to here for the next row of the periodic table. So we have sodium in here. All right. Okay, so we have sodium in here on the 3rd energy level. Magnesium has a greater ionization than sodium because it has more protons, so greater effective nuclear charge increases. But then we go to aluminum, and aluminum, even though the electron, we've got this more protons, it is less attracted to the nucleus than that of magnesium. And that is because of penetration. The p electrons are not cannot penetrate through the shielding as much as s electrons, resulting in less attractiveness. And so lower ionization energy. But then it's overcome by that increase in effective nuclear charge as you get more protons till you get to phosphorus. And then after phosphorus, sulfur's next electron is going to be not as attracted to the nucleus, even though it has more protons. And the reason for that is because of that first pairing of electrons. And you have that Coulombic force of repulsion between those paired electrons. But then again, it is overpowered by that increase in effective nuclear charge as you get more protons in the nucleus. And then after argon, the ionization energy would decrease because, again, you get another energy level. There is more distance between the valence electrons and the nucleus, resulting in less attraction. Okay, now you can see in the transition metals, though, that increase in the number of protons, ionization energy is pretty constant. And that's just something good to know. You might be asked about that, but they're relatively constant. And then again, the pattern picks up again. Okay, so how to explain these exceptions? The drop in ionization in between groups 2 and group 3 happens because the p electrons do not penetrate through the shielding of the core electrons as great as the s electrons do and are therefore not as tightly held, resulting in lower ionization energy. The drop in ionization energies between groups 15 and 16 happens because the increase in repulsion created by the first pairing of electrons in the p orbital outweighs the increase in the effective nuclear charge, and thus less energy is required to remove the electron. Again, these are going to be great ways for you to explain them when you're asked on the AP exam. All right, we do have some online practice for the trends that might be helpful in predicting what's going to be, which one's going to have more attraction than another. All right, let's talk about ionic radius. So again, the general trend for ionic radius is that it follows the same as the atomic radius. So as you go across a periodic table, the ionization energy is going to decrease. In general, there's kind of a start over point when you get to the nonmetals because atoms lose electrons. They're going to end up getting smaller, but nonmetals are going to gain electrons. So it kind of starts over with nitrogen gaining 3 electrons. And so then it gets smaller as you finish out the periodic table. So how to explain that on the AP exam? So cations are smaller than their neutral atom. The positive metal ions lose valence electrons. In many cases, this means they're going to lose the outermost electrons and are now in a lower energy level and thus much closer to the nucleus than the electrons in a neutral atom. So those electrons are going to be closer, more strongly attracted. Anions are larger than a neutral atom. The negative nonmetal ions result from the addition of valence electrons. But you still have the same number of protons. So increased electron-electron repulsion also causes the electron cloud to expand. All right, here we can just see a picture of atomic radius versus their ionic radius. So interesting here for lithium, and then after it loses an electron, just their relative sizes there. And you can kind of see that the size of a nitrogen anion is going to be larger than a lithium atom, a neutral atom. Now, electronegativity, that's going to be a big thing, especially as we get into bonding a little later on. If you're asked about electronegativity, again, the explanations are about the same. It increases as you go across a period because you get more protons, which results in a greater effective nuclear charge, which increases the attractive force of the nucleus and therefore strengthens the attraction for the electrons on the other atom that they are going to be bonding with. It decreases as you go down a group. Increased number of energy levels increases the distance over which the nucleus must pull, and therefore reduces the attraction for electrons. All right, so reactivity with metals. The thing you need to remember about metals is metals lose electrons. That's what they do. They love to become cations. And the more likely a metal is to lose its electrons, the more metallic character it's going to have, and is therefore going to end up being more reactive. So metals are more reactive as you move down a group. They get larger, and makes it more likely for those electrons to lose electrons. So because metals react by losing electrons, a loosely held electron will result in a more reactive metal. This is directly tied to ionization energy. With an increased number of energy levels comes an increased distance from the nuclear attraction, and thus more loosely held electrons available for reacting. Now, nonmetals are more reactive as you move up a group. So fluorine is much more reactive than iodine, if we just look at the halogens for an example. And that's because nonmetals tend to gain electrons. A strong nuclear attraction will result in a more reactive nonmetal. So fluorine has valence electrons in just the second energy level, high attraction for those valence electrons. So an atom with the highest effective nuclear charge and the least number of energy levels should be the most reactive nonmetal. All right. Now, steps for answering periodicity questions. Locate both elements on the periodic table. You want to talk about the energy levels. Where do they have valence electrons? On what energy level is it? And what sublevel, because that can make a difference. And do that for both elements. If they have the same number of energy levels, you need to justify with effective nuclear charge. So think about the number of protons. If they have different energy levels, then you're going to justify with the energy level of one versus the energy level of the other in terms of distance and attraction for that nucleus. All right.